Hi everyone, and welcome to the 2021 edition of the Computer System Architecture course. This is the first of a series of approximately 11 lectures that we'll be having together throughout this semester. Please note that this lecture is exclusively online, unfortunately, because I do believe that the very first lecture is always the most important one. Let's kick it off with a couple of words about myself. So my name is Hassan Soura, coming from France, and I've been and working as an associate professor at the German University here since January 2019. I hold a Bachelor Engineering degree in Computer Architecture, so this is exactly what this course is all about. I hold that degree from the University of Rennes. So for those who know France, Rennes is a city that is an hour and a half train ride to the west of Paris. I also hold a master's in critical computer systems and networks that I have from the University of Toulouse. So Toulouse is a southern western city in France, and this is the birthplace inter alia of Airbus. You know, the airplane manufacturer. And cherry on the top, I hold a PhD in software engineering from the University of Quebec in Montreal. And my thesis was about embedded softwares. I'm going to talk about those later on. Plus, we'll be having together normally in the next semester a course in embedded systems. So I'm also a nominated member of the Measurement Practices Committee in the common, called COSMIC, and it's the Common Software Measurement International Consortium, and I work there on delivering standards and norms on software measurement, and especially embedded system software measurement. Right, so prior to starting my work here at GUC, I used to work at ESTACA. So ESTACA is short for École supérieure des techniques aéronautiques et de construction automobile, which roughly translates into a superior school in aeronautic and automotive engineering, and that was in the suburbs of Paris. Prior to joining academia, I used to work as a research engineer in the electronic department, so in the advanced electronic department at the French car manufacturer Renault. This is why many of the examples that I'm having throughout my different courses, and especially the embedded system course, they stem from the automotive industry, so they're about cars and everything related to that particular world. I also worked as an R&D engineer at Thomson Multimedia. Now it's known as Technicolor. So basically, this is one of the TV manufacturers of many other appliances. And back then, I used on the predecessor of IPTV, so Internet TV. And I also worked at as a researcher in a national research center in France, in collaboration with Thales Avionics. So basically, I worked on advanced infotainment mechanisms inside, cabins. I also had the opportunity to work on autonomous cars in the French version of the Google car. Alright, so there's a French institute called Vidicom. It's the Institute for Sustainable Mobility Development, and I more specifically I worked on the safety of the autonomous car. So basically, I bet some of you heard about the problems that might happen whenever there's a autonomous car roaming around on the streets. So we need to make sure that both pedestrians and the occupants of the car, because we cannot talk about drivers anymore, they're safe in the different scenarios that might happen in real life. So yeah, my research. So next to the lectures that I give, I also have a couple of research fields. So everything related to the embedded systems. This is mostly my expertise. Or my experience, because we can never be real experts in anything because it's ever changing. So my experience is around embedded systems and in extension IoT, so the Internet of Things. Those are the small computers that are ubiquitous, so that you can find everywhere, and they're connected together in order to provide some services and have some kind of application. So we'll have plenty of time in order to talk about these throughout our experiences together, because we're having more than one course together. So yeah, so we need to have some kind of metrics, and we have to measure them in order to deliver some information and map some models. And I also naturally work on intelligent transportation systems, and these are the types of systems that you can find in cities today. And there's a lot of buzzwords going on, such as smart cities. So basically, whenever you're having something that is called an intelligent transportation systems, it's meant to be extremely smart in the way they commute people, workers, in order to make sure that it's ecological, it's quote green, it's sustainable, etc., etc. Then again, embedded system reliability. This means that in case of something goes wrong, well, we need to have some kind of system to make sure that a minimum service is still provided. And of course, two things that are extremely being deployed around the world nowadays, again, smart cities and autonomous vehicles. And by autonomous vehicles, not necessarily only cars, it could be drones, it could be bikes. So basically, there's a ongoing project here in the IoT lab that I'm currently managing here on a smart bike. So basically, a bike that gets to you in order to be able to ride it, and then it can help you out and detect blind spots and stuff like that whenever you're cycling, in order to make sure that this cyclist is riding their bike in a safe manner. So I get to publish a lot of paper, and I had the chance to win 2 Best Paper awards, and I also have 2 patents in my name as an inventor. Alright, enough about me now, and let's talk a little bit about this course. So the computer architecture course, naturally you have the prerequisites for the course, which are the computer organization course that you already have, and the DSD course that you normally had in the previous semester, in the first semester this year. And I've been told that the network people do not have the same DSD course, so I would like for those people to identify themselves to me or to any of the TAs that are listed here, so we can explain to you what are the proper measures and steps that you'll be taking in order to make sure that we are all on the same page. Fair enough. I also recommend, however, it's not mandatory, to get the textbooks or to have an insight about them at least. And you have the references here. Normally they're all available in the what do you call it, the library here at GUC, or in a way or another you might find them. And I don't necessarily want to know how you'll be able to find those. Right, so legally you will be you normally will be having them in the library here. Please do note that one of the things that I've throughout my 2-year experience here is people are extremely interested in the grade itself. I'm gonna get to that later, but however, if you want to know what is it that you'll need to take into consideration whenever you're preparing for the exams, so it's anything that might be said during the lectures, naturally the tutorials, the labs, anything that might be mentioned in the books or referenced in the books. And then usually we have a piazza for the course. Over there you have a lot of colleagues that will be asking most of the time very interesting questions, although sometimes they are kind of repetitive. However, the questions and the answers on Piazza are part of what's recommended in order to make sure that you fully comprehend and assimilate the course. Yep, this brings us to the grading, and yeah, you're gonna see a lot of those throughout my slides in the different courses, because I'm a big fan of memes. So yeah, and any original meme is also appreciated if you share. So yeah, I'll take that. Yeah, my piece of advice to you guys is not to overthink grades. It's not about grades. Grades are not the objective, it's just a result. It's a ripple effect. So my philosophy, once you're gonna graduate, grades do not really matter anymore, in the sense of good grades do not necessarily mean good engineering skills. So what I want to try and work with you is definitely your how to think outside the box. This might sound cheesy, but it is extremely important for engineers to innovate when it comes to solutions, to try to solve problems. So your problem solving skills, that's for sure. And generally speaking, I'm gonna put it as engineering skills, and I'm gonna use what I've learned throughout my experience, both in the industry and in the different international institutions that I worked in order to help you out and get those skills. Fair enough? So do try and enjoy the whole learning experience, so take it as a package, and I can guarantee that grades will naturally follow. So if you enjoy and you're motivated enough and you go ahead and enjoy the whole learning experience in this journey that we're gonna share together, systematically you're gonna get the proper grades, that's for sure. However, if you're aiming at the grades, you're gonna miss out on the things that you'll be needing later on in your professional life, or throughout your secondary, tertiary, whatever programs that you might be doing once you graduated from here. Fair enough? That being said, the percentages about the different types of things that will be graded. So we have a 2 out of 3 quiz scheme here that weighs 10%, then the midterm is 25%, naturally the final is 40%. And the lab work and the project, so basically we'll be having lab sessions throughout this course, and some of the lab sessions, the things that you'll be doing, the tasks that you'll be doing in some of the lab sessions will be graded and will be included in that particular 25%, in addition to the project that will be announced real soon on the CMS. Fair enough. Yeah, usually, and this is my piece of advice, always go for the first chance, the first version. Because in order to be fair with everyone, I consider that people who miss the first chance have more time to prepare for the second chance or the makeup or whatever, the second version of any exam. So in order to be fair with the first people, all right, they are usually a little bit more challenging. All right. So yeah, so let's talk a little bit about the course, the course's objectives. So we're gonna talk about computers, a lot of computers, in this particular course. And one of the most important words that I'm trying to make sure that people, once they're done with this course, they're gonna keep and use later on is performance. So what is performance? We're gonna find out what is meant by performance, how to measure it, etc., etc. So performance is one of the key metrics. It's one of the keywords in order to be able to compare different computers, different systems, different institutions, different. It's a way of quantifying different elements. One of the other major things that we'll be tackling throughout this course is how to translate from different high-level languages. So basically the things that you've learned so far, excluding DSD-CO, is maybe Java. According to my best knowledge, this is what you mostly do here at GUC, even though I really regret that you don't do a lot of C, because C is extremely important as well. So these are called compiled languages, and you have a different class of languages which are the interpreted languages, but this is not the objective of this course, so I'm gonna try and refrain myself from talking about these stuff right now. So how does a code that is extremely human friendly vis-a-vis the coders or the programmers, not some lambda human, of course, gets all the way down to the machine for it to understand it? So how does the translation mechanism happen from high level languages, right, such as Java for instance, right, down to machine languages, and how does the machine actually execute it? So this is what we're gonna see together throughout this course as well. And naturally, by now in your 6th semester, so this is your third year here, so by now you know that there's some difference between software and hardware. So basically we're gonna try and understand the interface between those two. So where does software end and where does hardware start? And how does software instruct whatever hardware modules that we might have in our computer to perform the needed functionality? And yeah, so one thing that might be curious enough is, why are we talking about architecture in a computer engineering track? It's weird to hear the word architecture. We're not architects. We're not going to build buildings or design cities or whatever. So why talk architecture? So we're gonna have the different nuances between what's an architecture, what's a microarchitecture, and what is meant by computer architecture. Fair enough? So we see an overview of the performance measurement. We're gonna have an idea about what's the memory and the memory hierarchy inside a computer. So I bet in CO and DSD you talked about different elements that are used in order to keep some bits, so we don't change states until something new is happening or something is enabled. So basically this is the cornerstone of memory, so we're going to develop it a little bit more throughout this course, but still it's still an overview, and you're going to have overview of the hierarchy and the whole system, but then you're going to develop it a little more in more advanced courses later on, maybe next year. We're going to talk about architecture, and from now on you must directly associate the word architecture with something called instruction set. So when we're gonna say architecture, we mean instruction set architecture, also known ISA. So from now on, ISA should something that sticks in your head, and we're gonna use it over and over throughout this course. And as an example, we're gonna use the MIPS ISA, and we're gonna find out what exactly is MIPS. Yeah, and then we get to the implementation. So in architecture, he could be seen as a blueprint, right? Something that has a different abstraction in a way or another. Fair enough. And then we're gonna get something concrete that is tangible. So basically the computers that you have at home, inside your phones, whatever, in your cars, for sure. It's something that you can touch with your own hands. So basically, yeah, so we're gonna implement an architecture. So this is what why we talk about hardware implementation, and notice implementations, because there might be different implementation for one single architecture. However, we're gonna talk about those more in detail throughout this course, so don't worry about that for now. So yeah, there are different possibilities for implementations. This is why we talk about implementations in plural. Fair enough. And if we have extra time, and I highly doubt it, we'll see by the end of this semester if we can add more stuff to the things previously mentioned here. Alright, I bet there are no questions, because if you do, all you have to do is ask me at the beginning of the first face-to-face lecture that should happen next week. Alright, so in today's lecture we're gonna introduce a little bit a couple of things. So we're gonna try and try to put in words what a computer is, because if we close our eyes and dream a little bit, we can all imagine what computers are, right? However, if you want to try and find words to describe those, it will be a little bit harder. So this could be one of the things that might change today. So we're gonna try and answer the question, the second question, which is where those computers can be found, right? And we're gonna check what are the different classes of computers, and we're gonna see what is meant by a class. Just from a historical perspective, we're gonna go and check a couple of examples of the very first computers. I mean, let me say that it's a selection of computers that are of my own interest, so throughout the timeline. So we're gonna find out about those in a couple of slides from now. They are particularly interesting, and they could give you an idea about the whole evolution of the whole computer industry. And naturally, we're gonna try and pin down what software is, hardware is, and what is the love-hate relationship that exists between the two. And finally, I'm gonna wrap it up with a pretty mathematical formula that will help us in measuring computer performance. So how to make the performance of the computer better, how to measure, quantify, understand performance. It's a kind of important aspect again, and it might sound that I'm repeating myself, but I mean, I cannot insist enough how this particular metric is important, right? So yeah, this is a joke, so please do not wash your motherboard. All right. So yeah, what is a computer? When was the first electronic computer incepted? So when was the inception of the first electronic computer? And I'm saying electronic computer because some might argue that the first computer was actually a mechanical one, and there's a history about that, but maybe it's not the right time nor place to talk about those. But it's quite interesting because in the looming in the city of Lyon, someone created a loom, and this loom was automated in a way using punch cards. So yeah, this was considered to be the first mechanical computer in a way or another. But here I'm trying to talk about the first electronic computer. So yeah, in the late 40s, this is where we had our first electronic computer. And you can see here a schematic, and yeah, you're gonna see a lot of those, and sometimes in your exams as well. Well, we're gonna try and learn how to decipher schematics and drawings and figures, and try to get some information out of them. So you can see here we're talking about the Industrial Revolution in a way or another, and you can see that there are four revolutions. So the first one was marked by the mechanization, the steam power, the weaving loom, as I told you earlier. So this is where we got things into motion. This is where you have your train, the steam train, right? And we got to mass produce, and not mass produce, but I mean the production could move, the people could move from place to place in a faster way, in a more secure way than before. And then came Industry 2.0, and this is where we started the mass production. And we tried to have assembly lines. So you know what an assembly line is people, it's elements or people or components lined up together, and then the first group of people, or first technicians, they will create something, second technicians will add another thing to that particular thing created, and then the third will add, etc., etc., and then at the end of the line we'll have the product ready. And then of course electricity was here, so basically this made things more productive. I don't really like to use this word this way because it's quite controversial. So it made things faster from a production point of view, but not necessarily more productive. Fair enough. Then in Industry 3.0, so this is considered to be the Industrial Revolution 3.0. It happened in '69, so this is a year that was marked by a huge event. Can anyone try and guess what that is? Yeah, so this is where the first men landed on the moon. Alright, so yeah, you can see here that computers, so this should be a T. So computers here and electronics in general, they played an extremely important role in that particular thing. So when computers and electronics are massively used in different domains and in places other than labs and stuff like that, this is where we had this milestone, which is Industry 3.0. And then Industry 4.0 4.0, and you're gonna, if you start applying for internships, or even later when you're gonna start applying for jobs, you're gonna see a lot of job offers with the keyword Industry 4.0. And a lot of times you're gonna see cyber physical systems. And by the way, I'm offering an elective course on cyber physical systems for the ninth semester students, and we can talk about those later on. So the Internet of Things, so this is another thing that is widespread today, and of course networks, etc., etc. So you people, you are in the heart of that particular milestone, which is Industry 4.0. Alright, so the third revolution for sure was marked by computers, by the massive use of computers, and most definitely the fourth, so Industry 4.0, is all about ubiquitous small computers being embedded everywhere. This is why we talk about embedded systems. So basically in smart homes, you're gonna find a lot of computers lying everywhere, in smart cities, in smart buildings, in smart offices, smart bedrooms, smart everything. So everything with the prefix smart to it, it must probably has a small chip or a small computer in it. And we're gonna talk about those in more details in the embedded system course later next year. Alright, so the first computers. Oh, let's see. So in 1940, the complex number calculator. So this could be seen as a calculator with extra steps. So it deals with complex numbers, and actually this is what you're looking at here is some kind of keyboard, a really vintage keyboard that is connected to a much bigger machine elsewhere through phone lines, phone-like lines, all right, or phone lines that are dedicated for a particular task. And then in Germany in 1941, you had the Z3, and unfortunately, I mean, this is the first real computer that looks like a computer that we're using today in a way or another. However, that one was completely been destroyed. Just notice from the date, it was during the Second World War, and during the bombing of Berlin, it got completely destroyed. And at the same time, and most of you have seen the movie about that, I think. So there's the bomb, and this is a computer developed in Great Britain in order to decipher the different Enigma messages that were created, that were sent back and forth by the Germans. Right, in 46 now in the US, there was a project called Project Whirlwind, and this is the first flight simulator. So you can see the whole computer occupying a whole lobby or a hallway, which is extremely unimaginable today. And this is a flight simulator, and today you can have a flight simulator on your phone, or your desktop computer or any gaming computer. The first general purpose computer is called the ENIAC, and it's short for Electronic Numeric Integrator and Computer, and was developed in 46 as well in the US. And and if you go to the museum over there, you can see it's still there displayed, if I'm not mistaken, in the MIT museum. And you can see that it occupied the whole room, and it weighed tons. It was extremely heavy, and it's bunch of wires and a lot of stuff. It's a nice scenery, and we came a long way since then. 48. The first computer with stored instructions. So it's called Selective Sequence Electronic Calculator. And until here, you can never store the instructions. So basically, you needed to feed the instruction manually to the computer. Fair enough? And then Great Britain again, and there's something called the Lyons Electronic Office, also known as LEO, so LEO. And this is the first management information computer, so commercial business applications. And I'm gonna give you 5 seconds to think about, so what kind of business was handled with that particular computer. And a hint, you can try and guess it from the name, because English people or British people in general, are very famous of consuming that particular produce. So yeah, you got it right. It's about delivering tea. So your tea and biscuits, they handled their customers as like a database and dealing with a lot of stuff, and with the addresses, etc., etc. What dealt with this particular computer. So the story continues in 58. Semi-automatic ground environment, also known as SAG. Alright, so this is, and again from the date and from the country, you can guess what that particular computer was used for. And this is a military, a man here. So that was a radar, a network of radars, in order to detect early USSR rockets or any aggression from the Soviet Union during the Cold War. And by the way, this is considered to be the first, or the predecessor, one of the predecessors of the internet as we know it today. Ken Back. This is the very first personal computer, so to be used at home, and you can see it's extremely small compared to the previous ones that we've seen. However, they were really unlucky here. They only sold 40 units of it or so, and they went broke. Alright, the Alto, made by Xerox. So yeah, it's starting to look like a computer, or at least, it gives the impression of a computer that looks like computers today. So yeah, you can see it as a desktop, and it has some user interface, graphical user interface, and it has some kind of mouse that could be attached to it. Right, so 78 here. So we're back to the locker with some components in it. And this is an important one, so I want you to keep it in mind for a reason. It's called the VAX 1178, but the VAX is more than enough. And this is a computer with such a good performance that it's 1,000 times, no, it's way better than any computer performance wise, than any computer that was created or proposed prior to that particular one, right? So there was a breakthrough when it comes to performance with the VAX. So for some reason, we're gonna keep it here and keep it in our minds as well. Alright, so the Osborne 1, this is considered to be the first laptop computer. And funny enough, this is the first computer that I've ever seen in my life. It was owned with, by my uncle, and I don't know if any of you, but no, I don't think so. But anyways, that was such a big deal to put your hands in a thing like that, and it's like a suitcase that you can carry around with you. It felt so weird. It felt like you're in a sci-fi movie whenever you get to play around with a computer like that. The Macintosh. So needless to talk about that particular one, but in '84, you see here, it's the computer that went inside every American home back then. Alright, so here you have the Next in '88, and when Steve Jobs was forced out of Apple back then, he created his own company and he proposed the first computer. That's funny enough. And then when Apple bought his company back, anyways, it's a long story. Sorry about that. So he innovated and he created the optical storage disk. So basically you can see it as the hard disk as we know it today, and there are some voice recognition technology and the use of mice and stuff like that. So yeah, he went rogue, and then he forced Apple in a way or another to take him back with his company. And of course we all know this success story, this professionally success story. And this looks like laptop computers that you'll be seeing, and it dates from 1991. I don't know how old were you, maybe in the negative years. However, this is, a computer that included a mouse, a roll here, like a mouse ball, and some hand rest here, so it was quite innovative. And then, since then, the story got more, dynamic, and we had more and more types of computers, etc., etc. So yeah, once more, keep that in mind. There's something called VAX, and it was really, really, good or excellent performance-wise back in its days. And we're gonna talk about that, and we're gonna see that later on throughout this course. Alright, so classes of computers. So unfortunately, because we're not seeing each other and it's not a face-to-face lecture, I am unable to get your your take on that particular question. So take it, you can pause the video and think about the different classes or different types of computers that exist out there. So yeah, sure, someone might say that, and of course I'm talking to the my fellow geeks. You can say that we have gaming computers and stuff like that. Sure, so this could be a category. Well, let's try to have generic categories or classes of computers. Alright, so pause the video, think about them, and then resume it in order to find out if you got them right. Alright, so yeah, PCs, personal computers, for sure. This is what you find, at home, sometimes here in offices, etc., etc. Fair enough. And then you have servers. So whenever you taking an online test or doing something, well, you're connected to a server. And this is another buzzword that we're using nowadays is the back end. So the front end could be anything that allows you to get connected to the internet in a way or another. Through the internet in a way or another. And then you have the back end, the servers that you're not seeing. Fair enough? Yes, embedded computers. So embedded computers are the small computers that you can find everywhere. So basically inside of your washing machines, in your cars, in an airplane, in your smartphone, in your smartwatch, embedded in the infrastructure. Every single small computer that is embedded somewhere is it belongs to the embedded class of computers. Fair enough. PMDs. So PMDs, let me take the smartphones out of the embedded computers for now and put it in the PMD class. because I'm gonna include everything that is portable, right? Mobile, get it? So it could be a smartphone, it could be a laptop, it could be a tablet, it could be anything, and you can use it in, you know, in a way or another as a personal device, and you can do it for use it for different things, for, let's call them, general purpose. All right. So yeah, a smartphone is probably a general purpose class of computers, unlike embedded computers that are usually specific for a particular purpose, but we'll talk about those next semester in the embedded system course. And finally, I'm missing out on one class of computers here. What would that class be? So if we have one server or two servers or multi-servers, right? There's another other buzzword that we can find in internship offers, job offers, stuff like that. And these are cloud computing. So clusters, warehouse scale computers. So something that is extremely bigger and distributed will belong to this fifth category right here. Fair enough? Alright, so let's have a look on that particular figure here. Well, it's a table, but I mean, it's still a figure. And try to compare and see what are the differences between the different classes that I showed in the previous slide. So pause the video, take your time to look at each and every row and column here, and then compare them. Fair enough? For instance, as an example, one way of interpreting and analyzing this particular figure here is to check the price of the microprocessor, right, in PMDs, the price of microprocessors in servers, right? So it goes anything between 200 bucks and 2,000 up to 2,000 bucks, somewhere around those figures here, and then compare it to the prices of the microprocessors of the embedded systems. So yeah, that's nothing. That's one it's extremely cheap compared to the prices of the microprocessors of the servers here. All right, and then sure, you can see the price of the whole system. And another way to analyze this particular price here, so you can see that my microprocessor, so the heart of the computer, fair enough, costs around this much, but it can go up to 10 millions. Why would the price of the system be much higher? So we can think about it when we're gonna see the design issues, for instance. So we can see that there's something that's called availability, scalability, and energy. Yes, servers do consume a lot of energy, not particularly because of the computation, but because of what? Take a second to think about it. What would cost a lot of energy when it comes to servers? And it's also true for when you go bigger. So one of the things is how to cool them down. Fair enough. And my fellow gamers, they know that we need to cool off the computers whenever we're over using it. Fair enough. So one of the challenges is how to cool servers down. So this is why we invest a lot of air conditioning and air cooling systems, etc. Or we can play it smart and do what? What can we do here in order to save a little bit on the energy consumption that might stem from using air conditioning? All you have to do is to implement physically the servers in colder areas, like in the Nordic countries, in Canada, etc., etc. All right. So yeah. So let's take a look under the hood of a computer. And this is one of the things that you should know by heart from now on. So logically, and the network people are kind of familiar with a layered logical schematic, which is the OSI layers, naturally. But anyways, so basically here you can see a layered view of a computer where we have two different categories of elements. So we have the hardware part, and then we have some kind of boundary here, and then we have the software part. And within the software part we have it's also divided into two different subparts here. Alright, so two different layers, which is the system layer and the application layer. So yeah, if I'm a human user, so where would I be? Will I deal directly with the hardware? I'm saying just saying a human user. I'm not saying an engineer. I'm not saying the technician who worked on the computer. Fair enough? So a human user, you know, anyone who might use the computer will be here. So they will be interacting with the application software. And then the application software will interact in turn with the system software that will in turn interact with the hardware. So yeah, each layer is providing services to the different layer in order to make it transparent from the user point of view. Alright? So yeah, so hardware is all about DSD and the stuff that you created over there. You can use VHDL, Verilog, it doesn't really matter. This is where you can find the different components, right, that you create. And this is what we're gonna talk more in details in this course. So the system software, this is exclusively your OS course, and you'll be having it with me as well. Lucky or unlucky, we'll see about that. Alright, so we'll tackle this part in the OS course in more details. And then the application, well, needless to say, this is what you've been developing till now. So it's any game, any Java program that interacts with the with the humans, with anything that does anything. This is application. Fair enough? But I need you to pay attention to that particular thing here, to this dotted line. What is that? Can anyone guess what that is? So this is the interface between the hardware and the software, right? So what's so special about an interface here? We should be careful about what here? So imagine that this is a French guy, and this is a Chinese guy. So if the French needs to talk to the Chinese in order for the Chinese to do something and then deliver it back to the French, right? Well, this particular guy here, which is standing on the interface, should do what? So we should go through them, right? So we should do what here? We should speak both French and Chinese. Fair enough? So this is the whole point of this course. So this is the CA. Alright. So yeah, so let's hit it off from high to low. So yeah, so this is C, but you can see that if you've all done some swapping in Java and methods and classes and objects, I don't really care. All you know that you created methods, so functions, fair enough. They are user friendly and they do something, and then what happens next? So try to imagine what happens next. Take a second or two. Let me get my laser pointer again. So we have the high-level language is compiled into assembly language. Some of you heard the word assembly before. Alright, so it changes format, however it does the same functionality, but you can see that we have more lines, different syntax, etc. So this is compiled, and then it goes through an assembler in order to get a string, a stream, let me put it that way, it's better, of ones and zeros. Why ones and zeros? Well, because machines, they talk in binary language. So DSD people they've seen that when we have ones and zeros, we get ones and zeros, and then with ones and zeros we can code virtually anything. Fair enough? So this is the exact same thing in three different syntaxes. This is very user friendly in the sense of it's quite understandable by a common, average programmer. uh, you know no offense for anyone, this is quite understandable with someone who might know the hardware world a little bit more, or the system software world a little bit more, and this is understandable by no one unless you're the one from Matrix, but this is just a movie. So yeah, definitely this is what the machine gets, and this is what the human gets, and in between the two there are the different layers that we talked about earlier. Fair enough. So yeah, where would you put the interface then? If it were up to you, where would you draw the line here? So where's my pen? Here it is. So where's the line? So yeah, so this is application, this could be system, and then yep, we can draw the line somewhere around here. Well, actually the line could include that one as well. So what is that? Where's the we can say that this is software for sure. Fair enough. This is software, but I mean it's lower level software. What about that one? Is it software or is it hardware? Drum roll. It is software as well. So basically, again, this is exactly what's written here, but this is understandable by the machine, and then it will run on. This is what will run on the actual machine. Fair enough. All right. So yeah, one of the things that you should definitely know by heart at the end of this course, I mean, starting today, why not, is the classical computer hardware components inside of every single computer that you might find out there. Yeah, so input, output, CPU, memory. Systematically, every computer out there has this particular logic. Fair enough. You can also add some stuff to them, but these are the classical ones. So let's see another more detailed schematic of this particular logical one here. So memory, let's try to map it. What would memory be here? Is it the sensor? No, it's not. Is it the output? No. Is the input? No. Well, it is the storage unit. Yep. So this is the storage unit. So another name for memory is the storage unit. And inside the memory, you can see that we have a primary, secondary, maybe third, tertiary, etc., etc. Fair enough. Output is outputs. That's easy. So this is where once you process things, you're gonna send them back out. And input, of course, is the things that you'll need in order to be able to process. Fair enough. And then you have the brains. Well, the brains is divided into a control unit and an ALU. So somewhere we're gonna do a lot of math, logical, mathematical, etc., and things that will control the lines. Whoops, what about the lines, by the way? What is another name for the lines here? So DSD people, CO people, you should know this answer. So this is a bus. Yep. Fair enough. So typically you're gonna find one or more buses, depends on the computer or the architecture of the computer, and you see those classical components everywhere. Fair enough. Speaking of which, we have two different architectures out there. Well, for now let's call them architecture, but the technical term and the exact technical term is microarchitecture, and we're going to see the difference between an architecture and a microarchitecture. To make a long story short, a microarchitecture is the implementation of the architecture. Fair enough. And the architecture, another name for it that I asked you to memorize for now and ever. So the other name of it, it's an acronym, it's called ISA, right? Instruction Set Architecture. Alrighty, so two major things we have the von Neumann and the Harvard architecture. So take a second to see the differences between the two, and take a second to analyze the differences between the two. Alright, so what is the difference between the two? First off, you can notice that in the von Neumann here, we have a single bus for both instructions and data. And both instructions and data are stored in the same memory unit, unlike the Harvard one. In the Harvard one, we can see that we have a different memory unit for instructions and a different one, another one. We have different memory units for data and instructions, and hence we have different bus lines, separated ones. Alright, so my question is, which is better? So systematically, whoever asks you this question in a way or another, you as engineers, you can never say that this one is better or that one is better. It all depends on the context, on the situation, on the application, on so many different things. Fair enough? However, I would say this one had more success, and this is the one that is implemented almost everywhere, but in embedded systems, which has something like that, closer to that. But anyways, in your personal computers, desktop computers, servers, etc., it's the von Neumann architecture that made it. Simply for a very simple reason is it's money oriented. It's about the cost, because here you're reducing the number of lines, hence you have less buses, right? So it will cost you a little bit less. So that was the drive of the selection of von Neumann in order to be implemented and widespread in the different computers that we have today. However, fortunately, and your generation of engineers, future engineers, I'm crossing my fingers, will not only be motivated by money, but there are different constraints, for the environment, so many things that we need to take into consideration, and not only how to reduce and cut off costs. Fair enough? So yeah, what would be the cons and the pros? So the cons of that one is we cannot do instructions and data at the same time, because we're sharing the same path here. However, here it's feasible. So this is a pro for this one, and this is a con. However, again, the cost here it's less compared to that. Fair enough? And you can think of other stuff. Alright, now performance. The question I'm gonna ask you before tackling this particular topic is: performance software a software thing, or is it a hardware thing? So again, feel free to take a couple of seconds to think about it prior to resuming the video. Yeah, because I bet that you had courses or at least some experience in the way you write code. So when you get to optimize your code, your program runs a little bit faster. Performs better. So let's say that for now, faster is better, whatever faster means, right? And some might argue that well, it doesn't really matter if we optimize our software. The machines are getting faster and faster, so it doesn't really matter. It's not a software thing. Well, is it though? So let's find out. Alright, so performance now, the performance chart, and here we can see the different milestones when it comes to computer performance. And what I want you to notice first is this axis here where we have the timeline for sure, but I mean more interestingly here we need to take a look at this particular axis. And what is the unit of performance? So here the time unit is in years, obviously. Here the performance unit is not really a unit per se, however it's a comparison to the performance of the VAX computer. So this should rings a bell. So remember the VAX that we talked about a couple of slides earlier? So this is the original unit of 1. So here you can see that performance 1 means that this is the original performance that is the benchmark for other commercial microprocessors that were introduced to the market throughout the years all the way up to 2018, and this is the time window that we're covering is 1978 till 2018. Fair enough? So it's relatively recent. Alright, so let's try and analyze this particular chart here. So you can see that there are different milestones in a way or another, and you can see that it's not a steady performance since the very beginning. There were different and there's a different pace each and every time we hit a milestone. So we can notice 1, 2, 3, 4, 5 different time frames. So the first one you can see we had an improvement of approximately 25% per year between 78 and 86, right? And this is majorly, the performance growth is attributed and driven by the technology. And then starting 86 all the way to 2003, right? It's roughly a 50% improvement per year, and you can see the frequency, it keeps on getting higher and higher throughout time here. So for the time being, I'm gonna associate frequency to the speed, right? So the microprocessors are getting faster, even though that this is not completely correct. This is only partially correct, and we're gonna find out why in the next upcoming slides. But for now, we can see that there's a increase in frequency, hence the performance got a little bit got better in the rate of 50% per year. So here suddenly the improvement slowed down a little bit, and it kept on slowing down all the way to recent years, where it's next to nothing today. Why is that? So let's see what happened here. Here we feel like we hit some kind of wall that made us slow down, and we kept on slowing down for different reasons that I'm gonna expose. Sorry, I'm not going to expose though. At least not now. In a moment. So yeah, so here you can notice that suddenly we had the frequency kept on getting higher and higher, and then it just dropped a little bit lower. And there's something in the naming here that is never, it wasn't mentioned anywhere here, and suddenly it started being mentioned here. So what is it? Can you figure it out? So take a second or two to think about it. So yeah, so here this was driven by technology. Here this improvement was driven by architecture, organization, new ideas, caching mechanisms, etc., etc., and increasing the clock, of course. But then here, the thing that we hit, we're gonna call it a power wall. So let's think about it. What power has to do with the improvement here? And why would it, restrain the improvement? So if you join your hands together and start rubbing them, right, faster and faster, you feel like they're getting higher and they're getting hotter and hotter, warmer. This is exactly what happens with a higher frequency. The what do we call them? The transistors. They keep on closing and opening and closing on a faster rate. Hence, they get warmer, hotter. They're gonna consume more power for sure, and they will produce more energy. Like thermal energy. So we'll have to deal with that as well. So we're gonna consume a lot of energy the faster we go. So yeah, came a time where we couldn't handle this anymore, in the sense of it's not useful anymore to go faster because we cannot handle it anymore. We cannot put cooling devices or make our processor go faster because it would just burn out. So the idea was to, instead of having one processor that does all the job, one really bulk or strong, powerful, whatever processor, that microprocessor that does all the job, why not just divide the jobs or on one or more microprocessors that work together hand in hand. So this is why you're starting to see here something that's called Core 2, Core Duo, 4 cores, whatever. So a core, for now, let's see it as a microprocessor, fair enough. So instead of having only one person dealing with everything in life, right, it makes more sense to divide life on different people. I only wish that is true, but anyways, you got the picture here. So basically, instead of having a overloaded CPU, we can have two CPUs, each CPU working in a 50% with a 50% load. We can imagine it like that for now. It's not, again, necessarily the truth, no real life, but I mean, we can see it this way. So that was the idea. All right, so let's try and go parallel, do things in parallel. So CPU 1 will do something, CPU 2 will do something else, CPU 3 eventually 4, whatever. It really depends on the number of cores that you might have in your system. Yeah, true, but something's fishy. What would be fishy? The fishy thing is, okay, so we went parallel, well, then we stopped here. We couldn't, we're not improving as we were improving between 2000 and 2003 and 2011. So what is it that that's stopped us from keeping on improving here? So the whole idea is, here we're doing some parallelism when it comes to the what do we call it? To the instructions, for instance. We can do things in parallel, etc. We can do data in parallel, for instance, as well. Right? So the idea is, we're doing stuff in parallel, instructions in parallel, instructions and data in parallel, but then comes a time where you cannot do stuff in parallel anymore. This is the maximum things that you can do in parallel. This is also known as Amdahl's law. All right, so you can search for it or look it up on your favorite search engine for now if you want to have more info about it, but you will tackle that in the microprocessor course later next year. Right, so you cannot juggle so many things in parallel because there's a limit to parallelism. So that's it. Everything that is we are able to do in parallel, we got to do it, and then there are things that are by nature serial and we cannot parallelize them, so no concurrency. So this is where we hit the limit. Fair enough. And that's it. This is the maximum things that we can do in parallel, and we're done. So we're dropped here, and here we are keeping on dropping. So even though we want to innovate and include some new ideas here, that's it. we've reached something here. What is that last thing that we reach here? Well, the last thing that we reached here is, if you ever heard of Moore's law. So Gordon Moore was one of the the founders of Intel, and he predicted back in the days that the number of transistors on a chip will double each 18 months, so each year and a half. Yeah, that's it. That's what I was looking for. Well, roughly. So basically, so things are getting smaller and smaller, and you can fit them on a single chip. However, you can imagine that because there's a limit for everything. So a limit for the power, limit for parallelism, limit for something else. What would that be? So the limit here is a physical limit. So you can get so much smaller, and that's it. Because imagine that if you go below a nanometer or something like that, well, the element wouldn't exist and be useful anymore. So we can go so much smaller, and then we're gonna hit the physical limit, and that's it. And this is what we're witnessing today. And this is why when it comes to general purpose computers or microprocessors in a way or another, right? So this is a quite flexible term that I might be using on purpose to say that, well, okay, so if you have a desktop computer equipped with a Intel Core 7, so this is the maximum performance that you might have now and in the future. So if someone would ask me personally, how to make things better from now on, because that's it, this is where we're at today. Well, I would say that if you want to do better, want to improve performance, you need to drop the general purpose. So you don't need to have computers that can be used for anything, but you need specialized computers that are extremely optimized for a particular type of applications or domain, right? Where you can just make sure that this is the best, this is where you can improve for that particular application or domain. And just to give you a hint, alright, so yeah. So this is exactly what I told you. So this is Moore's law, which is the co-founder of Intel, and he predicted that in 1965. So yeah, back in the old days. I wanna check another graph here, and let's try and understand it together. So what you're looking at here is the number of transistors per chip, and you can see that it kept on growing and growing. Fair enough. And this is up until 15, and you can notice that. I mean, you cannot notice it, but you can remember the from the slides, from the previous slide, that this trend cannot just go on because of the physical limits, of course. And here you can see the clock speed here in lighter blue here. Indigo. Is that indigo? I have no idea. Anyways, so yeah, you can notice that according to what we've seen earlier, and here we have a hint as well. So it's not about boosting the frequency of the CPU anymore. It's about having more than one core CPU, maybe with lower frequency, however with lower the load, so with half the load, or with a portion of the load that any of those previous generation CPUs might have handled on its own. And last but not least, this is the important thermal design power. So you can see it as, well, how much energy you'll be consuming whenever, in watts of course, you'll be consuming with your transistors here. So you can notice it follows the frequency of the transistors. It's the same trend here. So hence it's important to make sure that this one is stable and does not increase infinitely, and doesn't make any sense, because of course you're gonna end up with the burnt computer. All right. What else can I say about that particular slide? I don't see any. Yeah, maybe the number of transistors that are bought in the market, and you can see it's a very steep curve here, right? Then it started to whoop, just a little bit, a plateau here, and then it started to drop just a little bit. And then with the whole IoT thingy, it just went up again. Anyways, that's a different course, different story. All right, so as promised, and this is what I usually do, I take real life examples and things that you might encounter later in your professional life. So it's important for me to convey this particular a message and idea to you guys. This is what we call a, can anyone guess what do we call those here? The information about a particular processor. So the technical word is specs or specifications. Oh, we have it here. So specs, you run across this particular word a lot as engineers. All right. So these are the specs of the i7 9850HL processor here, and you can see. This is a screenshot, of course, from Intel. And you can see a different information. So let's try and go through the different ones here. Product, like, I don't really care about that. Code name, yeah, Coffee Lake. So basically, yeah, usually in companies you have code names for different products. That is also true in the automotive industry. So basically, whenever you're gonna buy, I don't know, a Megane, a Logan, or a Kadjar, for instance, from Renault, well, it's not the same name in the company. Sometimes it's called X something, etc. Yep, here you can see that to what class of computers it should belong in a way or another. Yeah, so it's meant to be included in embedded systems. So it's not a server. It's not meant to run in a server per se, but it's most probably meant to run in an embedded computer in a car or in anything in infrastructure, etc. So yeah, some logistics that I don't really care about. So status launch, this means that it's available on the market and it has been launched in the second quarter of 19, so 2 years ago. Lithography, you're gonna get back to that later. I like this one a lot because I worked in it. So they use conditional embedded broad market. So yeah, it's not necessarily in cars, it could be anything. So yeah, recommended customer price for sure. Oh yeah. Alright, so let's speak performance because we're interested in performance. Number of cores. Yep, so we have 6 cores. So this particular processor has 6 cores, which is awesome. So the number of cores, please note, this is important. These are the physical cores. So physically, if you open up the processor, you're gonna see physically. You would be able to touch if you had extremely tiny fingers and hands. 6 physical cores. Fair enough. So the load balance between the cores would be divided minimum by 6 minimum, theoretically again. So number of threads, well, please do not confuse threads here with the threads that we'll be talking about in the OS. So I don't want to use the term threads here. Instead of threads, we're gonna call them, let's say, logical cores, right? So these are physical cores and these are logical cores. Fair enough? We talk about real threads in the OS course, so stay tuned. So number of threads, we have 12. Alright, so we have 12 logical cores and we have 6 physical cores. So this is Intel, this is their architecture, their technology. You might have, you can see that the number of the number of logical cores is double the number of the physical ones. So each physical one is kind of logically divided into 2 logical cores. However, you could have, from a theoretical point of view, you can have a physical core divided into more than 2 logical ones. All right. And some companies actually do that, but I mean, it's not the issue here. Alright, so physical cores, logical cores, and then the base frequency, 1.9 gigahertz. Right? So all in all, in any as a whole, if you look at the processor as a whole, you'll be having that particular frequency. And then we have something interesting here. So if we have any fans of the Fast and the Furious franchise, you have noticed that sometimes their car they run on a certain speed, and then they can hit a button, and then they have some extra juice injected in the engine, and then it goes faster. Well, technically, we're not far from that particular idea or picture here. The idea here is, in some special configuration, we can get one of the cores to be boosted to 4.1 gigahertz, in a punctual manner for particular task or particular handling of a real-time job. All right, we'll talk about real-time in the embedded system, so no worries for now. Cache, cache is cache. For now, we can see it as some kind of proxy memory in a way or another, right? So if you ever use the web browser, alright, so that would be weird if someone answers never use the web browser. So we have some cache on the web browser, sorry. So the history of pages that you visited earlier, and they're there, and the whole idea is to make access to this particular web page faster. So it's the same principle. Bus speed, so this is how many how many bits can be sent on the bus, how fast the transition of the bits happen on the bus. And another name, well, again, we'll talk about that in the embedded systems for now, so let's stick to the bus speed for now. And the TDP, what would that be? Let us think for a second. So T would be temperature? No way. So it's in watt. Oh, alright, so I remember something about that. So P could be power because it's watts here. So the T would be thermal design power. Fair enough. So how much power we'll be consuming when we run at the base frequency, which is 25 watts. It's, to be honest, maybe in the next lecture I'll show you a video of someone cooking some pizzas or some meat on a microprocessor. Yes, we used to have fun sometimes doing that. Alright, so remember lithography from the previous slides? So what is lithography, and to be more specific, photolithography? I'm getting tired. So in one word, lithography will be the printed microprocessor, so the size, the dimension of the microprocessor. So the whole idea is just to give you a taste of it. So you see your motherboard, the chips, the chips that are on your motherboard. So the different we call those die as in DIE. I mean die as in what would be a common name for those? So this is the component. Yeah, that's a common name. So the component that you see in your electronic devices, right? So actually those components are made out of sand. Yes, common sand that you find on the beach and in the Sahara here, for instance. However, they need to be purified. So from sand you get something that we call an ingot in English, right? And then you slice it into wafers, and on these wafers you're gonna print out you remember the design of your microcontroller, and add layers to it in order to get the final component. And adding the layers, it just looks like adding toppings, cheese and sauce, and to the crust, right, to the pizza here. So it is the same thing. So we have aluminum, silicon dioxide, some other chemicals, right, in layers in order to get the component. So hold on a second. So this is all nice, so we can consider that like a piece of paper that we're printing something out on it. So where is our blueprint? Where is our original copy? Where does this happen? Yep, it happens on a particular you know element. I'm gonna call it for now like that, it doesn't really matter. So it's some kind of plate, right, on which we're gonna design the system, put it in a special machine, right, and then this could be seen as a printer, right, that will print everything on the sliced wafers. Fair enough? And I'm talking to you about this because if you check this picture here, you're gonna see a young version of your tutor, right, that dates from a while ago now, 2005. And here you can see the lingots, right, so the wafers being organized in order to be put in the machine in order to print out the microprocessors. Alright, last chapter in today's lecture, which is extremely long by the way. Anyways, we had so many things to talk about. So how can we measure performance? So we had an idea that it should be related to frequency in a way or another, but should it just be frequency? Alright, so performance is actually measured in time, right? So from now on, whenever someone mentions computer performance, it should be relative to time. And we're going to call it response time or execution time. And in it reflects the time that runs between the start of the execution and the end of the execution. Fair enough? Yep. Start and ends and finish of an execution. Execution of what exactly? So yes, this is a very legitimate question that one might ask. Keep that in mind. Another way to measure performance, well, it's could be seen as how many things I can get over in a given time. So here it's using a timer to say that, alright, so go and stop, and we can see how much time you've taken in order to finish a job. And here we're gonna say that given 10 seconds, how many things can you how many hot dogs can you eat, or how many pizzas can you eat? All right, so the amount of work that you can do in that given amount of time. And this is technically called throughput or bandwidth. And actually there's some kind of difference between the two, but it doesn't really matter. Maybe the network people do know the difference between the two. So maybe next time in our face-to-face lecture someone will get back to me on that and to see if we're on the same page. Alright, so that's interesting. So this is the throughput, so how many things I can finish on time. Alright, so it's either time me or time the things that I can do in a particular time. So yeah, response time of what kind of job here? We'll answer that. So yeah, remember the classes of computers that we talked about earlier? So give it a thought for a second. So the number of work done, or the amount of work done in a given time, is more appropriate for which class? Think about it for a second. Is it the desktop PC, your personal computer? Is it the embedded system computer? Is it the servers? It is the servers, because usually using servers, well, you're trying to do multiple things at a time. So the idea is how many things I can do at a time, right? How many things I can handle, within 10 seconds or 5 seconds. Unlike embedded systems where you have, to respond to some special demand, as fast as possible. Let me put it this way for now, and we talk about again that later in the embedded system course. So yeah, so embedded systems would be, it would be more appropriate to use response time for embedded systems but it would be more appropriate to use throughput for servers or maybe cloud computing, computers, etc. Yep, so performance is 1 over execution time. Execution time usually in seconds. Well, any kind of unit, but seconds. Fair enough? It could be microseconds, picoseconds, doesn't really matter. Even hours, doesn't really matter. But I mean, it's relative to seconds. Fair enough? So it's wall clock time. So according to that particular equation, what can we say? We can say that the faster the system is, the better the performance, right? So the smaller the execution time, the higher the performance. Fair enough? So if you got that, let me give you a riddle here, a quick one. So if someone says that computer B is n times faster than computer A, so how would you define n? So use execution time, stuff like that. So you're on the clock. And yep, so you can see that execution time of computer A over execution time of computer B is equal to n. Fair enough? So yeah, the smaller this is, the higher n is. So the smaller the execution time of B, right, the higher the computer the n. So let me get back to the frequency and the execution time. Alright, so up until now we all know that we have frequency in a computer. Fair enough? And the frequency is usually generated, not usually, it's always generated by a clock, some kind of clock, anything. It could be a resonator, a crystal clock, it doesn't really matter. Right? So we have some clock cycles. So what is a clock cycle? So by now, especially the DST people, you know that we have a rising edge and a falling edge, and between the rising and the falling, well, this is a clock cycle. Well, the idea is, well, what am I trying to do in a clock cycle? So what I'm trying to do is to execute something, because I'm a computer, so I'm going to execute some instructions. Fair enough? Where do I execute my instructions, by the way? Inside the CPU. So I can get something from memory and execute it. We'll talk about that in more details later. Alright, so the whole point is the execution time that I'm trying to keep track of is the execution time of a bunch of instructions. Fair enough? Well, another word for a bunch of instructions is a computer program. Get it? Awesome. So we have a bunch of instructions that we want to execute. Well, one instruction might take one or more clock cycles. Fair enough? So in addition, for instance, and I'm saying something extremely stupid, but I'm gonna just give it as an illustrative example for now. In addition might take one clock cycle to execute fully, to finish, right, until the semicolon. And maybe, again, something stupid, a division might take 2 clock cycles. Fair enough? So it will need rising edge, falling edge, rising edge, falling edge again to finish its execution. So the whole idea is to try to find out which type of instruction will take how many clock cycles. And this is how we will be able to predict or even measure performance. Fair enough? And of course, well, I'm generating some clock cycles, so rising edge and falling edge. Well, how close the rising edge is from the falling edge? Well, this is dictated by the frequency. So the faster the faster I open and close, the faster the clock is. So the smaller the clock cycles are. Get it? If I have a real slow clock, well, the clock cycle will be, longer. So this is it. So clock cycles related to frequency, and we need to know the clock cycles taken by each instruction to know what is the total execution time. So frequency is 1 over time, right? So this is where we're gonna get our seconds from. This is where we're gonna, this is related to this. So these are our seconds, and then using the number of instructions, and especially the type, and notably the type of instructions, we're gonna find out, well, how many clock cycles in total we need to execute the program. Hence, what is the execution time of the program. So keep that in mind. This is one of the major things that you need to keep in mind forever and ever and ever. So CPU execution time is whatever instructions we're trying to execute multiplied by CPI. So what would CPI be based on the things that I just told you? So CPI, C most probably is going to be clock cycles. So how many cycles per instructions? Fair enough? Awesome. So if we have 10 instructions and each instruction only takes 1 cycle to execute, well, we'll need 10 cycles. And if the frequency is whatever, a 1 hertz frequency, so we'll be having 10 seconds in order to execute. We good? Alright, so I want to try and explode now the equation from before, and I'm gonna officially call it the performance equation. Fair enough? So the performance equation is execution time, because we said that performance is 1 over execution time. So execution time is all about performance, and the other way around as well. Okay. In seconds per program, because a program is just a bunch of instructions, fair enough, would be, well, the instructions that are found in the program times the clock cycles needed by those instructions to execute. If there are multiple types of instructions, this should be taken into consideration as well. And then the frequency, well, the frequency is nothing but how long is the clock cycle, so it's seconds over the clock cycle. We got that? Does it fit? Let's see. So it's seconds, right, per program. So program, we have it here, instruction, it's gone, clock cycle is done. So we're ending up program, seconds over program, which is perfect. Alright, so I'm putting that on purpose because each and every time, you will remember this meme better than the equation. So each and every time you're gonna talk about performance, you just look at the time, so the execution time. We good? And that's it for today. If you want to go the extra mile, you can go and check on your favorite search engine the different microarchitecture models that we introduced in today's lecture. If you still remember the names of them, well, it's Harvard and von Neumann, but you can go ahead and check if there are some kind of hybrids or other models that exist out there. Should you have any questions, I'll be glad to answer those in our first face-to-face lecture next week. Have a good one and see you very soon.